Hey everyone, and welcome. Let's dive right into this explainer and look at a massive, massive traffic jam happening right now in our green energy transition. As an educator and energy expert, I see so much focused on building flashy new solar panels and wind turbines. But today, we're going to talk about the physical backbone that makes all of that actually work. We are talking about grid-enhancing technologies and why modernizing the power systems we already have is literally the most critical hurdle we're facing today.
It's kind of a crazy paradox when you think about it. We have gigawatts of wind and solar ready to go. Incredible renewable projects are just sitting in interconnection queues. But our congested transmission grid is forcing system operators to just throw away or curtail perfectly good, clean energy. And why? Well, because the physical wires simply cannot handle the flow. The energy is absolutely there, but the delivery mechanism is completely blocked.
So, here is our roadmap for today. We'll start with the grid congestion problem, then get into grid-enhancing technologies explained. From there, we'll look at dynamic line ratings, power flow control, common mistakes and challenges, and finally, 5 steps to grid success.
All right, Section 1, the grid congestion problem. To make sense of this, let's use an analogy we can all easily understand: highway traffic. The bulk power system operates a whole lot like a massive road network, and right now, it is suffering from severe rush hour gridlock. So when traffic gets bad, the traditional old-school solution is to just pour more concrete. In the power world, traditional upgrades mean building entirely new transmission lines or doing what we call reconductoring, which basically means physically replacing old wires with new, higher-capacity ones. Both of these are exactly like adding physical lanes to a highway. They are incredibly expensive, they face huge permitting hurdles, and they take literally years to finish. But grid-enhancing technologies, or GETs, take a totally different approach. They act like a smart, real-time traffic system, using software and hardware to maximize the capacity of the grid we already own. Which brings us nicely to Section 2, Grid-Enhancing Technologies Explained. Because rather than spending a decade permitting a new line, we can actually deploy this smart technology today. How does the whole shebang work? Well, there are 3 main pillars of GTS at play here. First up, dynamic line ratings, which measure the true real-time capacity of our transmission lines based on the weather. Second, advanced power flow control, which actively reroutes power from heavily congested lines to underutilized ones. And third, advanced topology control, which uses software to identify clever grid reconfigurations that route flows entirely around bottlenecks. Together, these 3 things form a highly responsive, genuinely modern grid. Let's move to Section 3, Dynamic Line Ratings. We're going to see how this first major technology turns static, rigid infrastructure into a totally dynamic system. So, the crucial takeaway here is that DLR acts a lot like variable speed limits on our power highways. Traditionally, utilities use static line ratings. They assume a worst-case scenario, like, say, a blisteringly hot, completely windless summer day, and they permanently cap the line's capacity based on that extreme assumption, just to prevent the wires from overheating and sagging dangerously low to the ground. But come on, most days aren't worst-case scenarios. DLR safely allows a percentage increase in capacity by constantly monitoring the actual real-time conditions. Now, if you want to understand the core metric behind this, don't worry, we aren't doing any heavy math today. Just remember this conceptual KPI calculation, the heat balance equation. A power line's capacity is basically a constant physical battle. On one side, you have heating, which comes from the electrical current flowing through it, plus the heat from the sun. On the flip side, you have cooling, provided by the ambient air temperature, and, most importantly, the wind. If the wind is blowing, the line is actively being cooled down, meaning you can safely push a lot more power through it. It's that simple. For a practical, real-world example, consider tension-based monitoring systems like the Nexans Cat-1. Instead of just guessing what the weather is doing, operators deploy remote monitors out in the field to physically measure the tension and sag of the line in real time. They shoot this critical data straight back to the utility's control center, allowing grid operators to safely increase the line's power rating when the conditions are right. Moving right along to Section 4, Power Flow Control. If DLR is a variable speed limit, then these devices act as the traffic cops actively managing the flow of the grid. In a traditional AC power system, electricity is pretty stubborn. It just follows the path of least resistance. Historically, we haven't been able to tell it where to go, which means one line can be completely, dangerously overloaded while a parallel line right next to it sits completely empty. Power flow control totally changes the game by altering the electrical reactance of the line. Using modular hardware, operators can literally push power away from a congested line and pull it onto those parallel lines that have spare capacity. And the real-world results of this technology are just staggering. Utilities aren't just talking about this in theory anymore. The UK National Grid used this exact tech to accelerate wind power integration, completely avoiding the need to construct new lines and unlocking massive, massive consumer savings. The Far-Cross project over in Europe significantly increased cross-border power capacity. And in the US, Central Hudson used modular power flow control simply because it takes up way less substation space compared to large legacy fixed series capacitors. Grid operators are achieving immense efficiency gains from the grid they already own. But of course, we need to hit Section 5, Common Mistakes and Challenges. Because, let's be real, if these technologies are so amazing, why aren't they absolutely everywhere yet? A super common misconception is the assumption that DLR is some magic wand that always increases grid capacity. That is a total myth. In reality, during a really hot, windless summer afternoon, DLR will often dictate a lower capacity than the traditional static rating. But actually, scratch that. That's not a flaw, that's a brilliant feature. It gives operators the precise situational awareness they need to keep the transmission lines from literally melting down or causing a public safety hazard. DLR isn't just about capacity. It's absolutely crucial for reliability. Nope. Beyond weather dynamics, the biggest hurdles to widespread adoption are actually human and economic. System operators are naturally pretty conservative, right? Their main job is keeping the lights on. So they're often super hesitant to trust fluctuating real-time software limits over the fixed static limits they've relied on for decades. Plus, traditional utility financial models incentivize massive capital expenditure. Simply put, under the current rules, utilities often make more money by building a really expensive new transmission line than they do by buying highly efficient optimization software.
So how do we actually overcome these hurdles? Here is Section 6, 5 Steps to Grid Success.
To really succeed here, we need a coordinated action plan. 1. Operators must deploy sensors to monitor local weather and line sag dynamically. 2. We've got to install modular power flow control hardware to actively route energy around those bottlenecks. 3. We need to utilize smart software to constantly optimize the network's topology. 4. Utilities absolutely must upgrade their legacy control room software, their SCADA and EMS systems, so they can actually accept and use this variable data. And 5, perhaps most importantly, policymakers must realign financial incentives so utilities are rewarded for efficiency, not just for pouring new concrete.
I think this quote from Michael Passin at the Department of Energy perfectly summarizes our deep dive today. He says, "The delivery system is the crucial foundation. We can build all the wind and solar generation in the world, guys, but if we don't modernize this foundation with smart, grid-enhancing technologies, we simply won't achieve our clean energy goals. It's time to work smarter, not just bigger."
And so it begs the question, are we going to keep trying to pave over the energy crisis with more concrete, or are we finally ready to build the smart grid of the future? If you found this explainer helpful in breaking down the complexities of our power systems, please hit that subscribe button and join our channel community. I would absolutely love to hear your thoughts, so let me know in the comments below which grid technology or renewable energy hurdle you want me to break down for you next. Thanks so much for learning with me today, and I'll see you in the next one.